Hello, sir, am I audible?
Yes, you are. Please go ahead.
Okay. Is this visible? Hello?
Hi everyone, I'm Hemant. This is my teammate Snega. Today we will be discussing the topic model uncertainty based rewriting for robust convergence. So our TA mentor is Prateek Chanda, and now a brief outline of this talk. So we will be starting off with why this particular work is being done, and three papers that are in this direction of work, and also finally the concluding remarks, and also update on the project front. So now coming to the motivation, why exactly do we need this rewriting strategies and all? As we all know, LLM pre-training is basically done in two phases. One is data curation, specifically. So basically, it is huge or massive data sets which are crawled from the web, and next we will be doing a training with uniform sampling on this constructed corpus. So the problem here is that since we are scraping or crawling from the web, so the data will be having a lot of redundancies and also some noise. So, but while we are training the model, right, we'll be giving equal importance when we are updating a model to each and every sample, even the noisy and the clean ones. So in order to mitigate that, we use these model uncertainty measures to weigh the samples and come up with some scores that can say to the model that this sample is important and this sample is not important. So how do we get based on this uncertainty measure as our signal? We try to come up with a way. Should it is showing it's just it. Okay, so the common way that we can get the signal from the model is using loss and gradients of it. So how do we do that is what the next three papers that we are going to discuss talk about. So the first paper that I will be discussing and the next two, my teammate Snega will be discussing is the first paper is self-influence guided data rewriting for model language retraining. It is published in EMNLP 2024 and it is by Google. So the motivation for this particular work, as I mentioned, uneven quality data. So to give weight and all, we are leveraging the gradients of the particular sample to get the weight for that particular model. So that is why the word self-influence. And inefficient filtering. As I said before, since the data sets are very massive and manually coming up with some heuristics to do this weighting is not a realistic approach. So one more thing is one more problem that we generally face is static sampling limit performance. So that is traditional pre-training treats all the samples equally. So that is one of the main motivation for this works, right? So now coming to this work, we try to come up with a framework that tries to assign weights automatically to the sample. So how do we do that? So one particular way is track and score. This track and score proposed by Pruthi et al. Computes the influence. So basically what it the information that it gives is how much the performance on the test sample is influenced by the training sample at a current time step. So as you can see, this particular formula, the track-in formula that you can see here is derived from first order gradient approximation of the update rule. So now coming to self-influence, the self-influence score gives how a sample has effects on its own. I mean, when you are adding a sample, how much effect or how much influence does it having on the model performance is what this self-influence score gives us. So, but how do we know, or what sort of correlation is there between the noise in the data and the SI score? As you can see in the graph below, there is a clear correlation that on the left, you can see the noisy text are having high SI scores, and the clean text is having low SI scores. This clearly gives a signal that we can leverage some information with this SI score value and segregate the data into noisy or clean. Similarly, in domain and out of domain, F is the model with parameter theta. G is the gradient function. Can I go ahead, sir? Yes, yes. Yeah. So generally, if a model is doing bad, the loss will be bigger, right? So obviously, the gradient with respect to the particular sample will be bigger. So basically, that's sort of an intuition we can get. That is one sort of motivation that they are trying to come up. There is one strategy that they are coming up. There is a strategy that they have proposed. Yes, sir, I will clarify. Now coming to the first type of framework that they have called, that is present sequential, where they'll first train the scoring model and then retrain the model. So here they initially start off with MC4 data set, and they randomly sample some before pre-training it. They randomly sample some instances and they train a scoring model. So the scoring model that they have used here is MT5 base model. So using this, we come up with some scoring function model that gives score to the entire corpus and segregates our entire corpus into such things as a score high to low. So now from the previous graph, we can conclude that low SS score implies clean and easy data sets for easy samples. So using this, we will try to pre-train the final model. This is one framework that they have said. Sir, she is working, so I will give more reasoning to that in the next slides. Yes. So the next one is the presence. So here what they do is, as you can clearly see in the previous framework, you have to wait till the entire scoring model is trained to start your pre-training. So this particular presence, this framework tries to um, do both waiting as well as pre-training simultaneously in an online fashion. So as you can see, we'll start off with the initial random initialization model, and then we do a batch waiting. I'll talk about it in the next slide. And we get some SI scores. So based on this, we try to update the model. So we do this steps. We repeat these steps for some time. This is what they call direct weighing. So here the SI score directly will be given higher weights. So the direct weighing means a higher SI score implies high weight. So directly proportional. So after doing for M steps, you end up with some model, and then you do what we call inverse weighing. So there the relation is inversely proportional. SI score high is implies low weight to the sample. So now the question is, what is this batch weighing and what is this different type of weighting, direct weighting and inverse weighting? So now first, what is batch weighting? So here, as you can see, computing the gradient or getting a gradient for each sample is computationally heavy actually. So what they try to do is they come up with something called this mini batch level reweighting strategy, where they are trying to get the SS score vector, the this capital S, and they are trying to normalize it within that sample, uh, and then they are getting a softmax score. While calculating the softmax score, they are taking a temperature variable, depending on which we control the type of weighing that we are doing, either direct or inverse. So based on these weights, you take a weighted sum, and that is going to be your final gradient for your batch. So this is what batch weighing is. And coming to direct weighing and inverse weighing, as you can see in the graph below, the general trend is that the model training loss, the sample, what they meant is batch. Yes, yes. Softmax of the SS course. Yes.
In the last feature,
Yes. Like
they're normalizing within a batch.
no. So this is a sentence.
smaller.
I took it.
What is smaller?
Small and nowhere small.
So actually, this particular algorithm is for one big batch B, and for every micro batch they take within that, they're saying. So for a particular batch only, they're normalizing it.
Like, it's like,
Yeah, n samples are in a batch.
well, you some max, everything like,
Yeah.
and you gene is for
Hmm.
a microbatch.
D is for micro batch. Yes.
G is a gradient.
These are gradient for each and every system.
Sir, so the capital G is for mini batch and small g is for micro batch. Yes.
Yeah.
Yes. 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 Yeah, you can say, but there is one more thing that they are saying micro batch. That is, yes, yes. So now, why direct reweighting and inverse reweighting? So the graph says initial steps, the model is learning all concept fast. So that's what they are concluding from the graph. So right. So what they are trying is they are forcing the model to learn hard and noisy concepts fast. So for that they are taking this directly proportional here. So that means higher SS score implies higher weight. So that means the noisy or hard samples are given more weight here. Now coming to inverse weight, so the relation goes faster. So as you can see, the loss is not dropping fast as training steps are increasing. So here they are inverting the relation by inverting the sign in the temperature. In the softmax calculation, based on the temperature, you can control the reweighting. If you can see here, the temperature equation, if you sign, if you so these are the data sets that they have used, and they have taken 5 tasks on 5 data sets for 3 tasks, and these are the results and some ablations and all they have done. But, so we found out these are two are the main limitations. So there is no clear distinction between noisy and hard samples here. So when you are doing this temperature sign shifting and all, we may not know the what is noisy or what is hard. We may be losing out on hard instances as well. Fluctuating and inverse. Yeah. Yes. Yes. So they have done this. You can see the table here. They have done different type of things. But as far as I see, they didn't mention anything about when to switch or something. Uh, One is D in the sense direct reweighting. Model pre-trained completely on direct reweighting. I is inverse reweighting completely on inverse reweighting. ID is first inverse, next direct. The normal one is direct followed by inverse.
they chose based on heuristics.
They haven't mentioned any rule or something. Yes.
But if they're on the B, as writing. B there. I think B was
Yes, that I am not sure, sir. Yes. Yes, yes, yes.
that I think bring the next.
Hmm.
Yes.
Yes, sir. So they were saying this particular frame is highly task specific. So which type of reweighting or what you are doing? No, sir. They are doing that. The proposed framework is DI. The last row. Yes. Yes.
And like from B version. Because they only play in tasks. They are not even a recipe for vendors.
No, 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 sir. No. Yes, and the next paper, Snega will decide. Okay, this is correct.
Machine learning. So main operation of this work is if we see traditionally we try to minimize the numerical but in later development we can create a sequence between all the samples. So when that situation like we have very less data or any distribution is one. So one compare the equation with others. So distribution of this so they got including so the first equation over here is the primary problem. So what they basically do they can minimize the loss. Model the most scale data distribution data contribution in it. So B over there is valuable measure is the measure how the data but what's more interesting what's we are your phone for these are applications. So that's make it at they're taken from this.
So these guys. What I think that's this.
Perturbated. Instead of taking. Yes, yes. So instead of taking all possible P dash, instead of taking all possible P dash, they are trying to use primal dual form.
But especially don't
No. So we have instances, right? But we don't know the underlying distribution. So we are taking expectation over all the instances that we are having that follows that particular distribution.
each and every sample Z.
Because Z follows the distribution of data.
Sample over sample of
Yeah, it's copied from the paper.
We are taking infimum over all lambdas, right? No, infimum over all lambdas possible, all positive lambdas. Really?
I'm not sure. We didn't see that. That's what they mentioned in the paper.
And voila. All
They we see the term inside the dual, it kind of acts like a weight term. So f star of inside that we have a loss, normalized by some constant over there. So they are saying it kind of acts like a weight over there, which depends on the loss, for example. Lot of paper based on this DRO, but major drawback this paper addresses from those works is scalability and robustness of outliers. So when it comes to this primal form, we can see that we have to maintain the data distribution over the complete data set, but that is not feasible when the data set is huge. And in case of dual form also, gradient estimate is not a trivial. So one more major drawback to this DRO is it doesn't address the outlier. It just upscale the weight based upon the loss. So noisy sample also have high loss and hard sample also high loss. So noisy sample is also being scaled here. So that shouldn't be happening. So how this paper addresses this is basically the first one is the same objective I showed over there. So P is a divergence measure. So one of the divergence measure, these people they are assuming tail divergence over here. So after some methods, we can actually approximate to this function they have given. So, and the algorithm I've given over there is basic gradient descent algorithm, like the way we update the model. And coming to the outlay, like how are they dealing with noisy function? They're doing weight clipping. So since the weight depends upon the loss value, if the loss value is greater than some theta, like it basically, sorry, tau, it basically clips over there. So that's one of the way they're dealing with the outliers. And coming to the gradient update, this is the equation we can see. So like traditionally we just have this gradient with respect to loss and we just multiply the learning rate and then update it. But here we have a weight which is nothing but we are exponentiating the loss and multiplying with some gamma over there. So in this algorithm, the steps are basically same as stochastic gradient descent, but two hyperparameter we have to be careful of. One is the tau, another one is the gamma. So if we see like how do we set those, like basically I've set tau as 1 and they're changing the gamma. So the performance of the model is not much varying, like there's a very little variation. So gamma is little bit invariant to whatever we are doing, given the tau is 1. So that's what they're set for the rest of the paper. And they have applied this method on the supervised learning, meta learning, and out of. Yeah, RGD, tau equal to. Minimal, yeah.
Same thing for downwards also.
But the performance, if we see how equal to 1 have better than the 3. This specifically they don't do on the pre-training setting, they do on this supervised meta learning and out of domain distribution. So yeah. And they're using KL divergence over here. They've not assumed any, they're both F divergence and they come to that thing. They won't assume anything KL divergence over there.
Just in the supremum, you have the D function.
So, like we can see that, like one of the unique thing is that weight clipping only, to be frank, to see the taper. So that actually makes the model perform better in all the settings. Again, outlier handling they're doing with weight clipping. They could have went with more principal approach. Other one is, again, it will only handle the variant noise, but it won't handle any adversarial or systematic noise. The third paper is dynamic loss-based sample reweighting for improved language model pre-training. So it's a recent paper in ICLR. So the main thing is, usually in case of pre-training, majority of work is focused upon how do we mix the domains. So here, they're basically going on the fine-grained level of how do we give weights to each and every sample instance based upon the sample loss. So also the question is, since it is pre-training, the dataset will be huge. So how do we do this dynamically without computationally overhead or any extensive other things? One of the main challenges over here is we can't um, we can't go with the training heuristics to come up with a weight loss, because in case of LLM we have a very large data set and mostly it will be like once in a cycle the data point will be seen. Another one is we can't use a small holdout validation set because again it won't capture all the diversity present in the data set. So how are they coming up with? So here their main paper is based upon like motivated from this first theorem. So they're assuming the function to be convex, but they've shown also in the non-convex set also. So this basically says the bound on the convergence of the convex function in the reweighting setting. So the one in the RHS side, that delta is, if we see the delta is basically, it's a gap between the optimal value for theta and the one at a theta time step t and the weight term over there. So basically, you is affected by these weights we give. So that's the main motivation they took, and they came up with some strategies. So before applying weights on the loss, they're normalizing the loss between minus alpha to alpha value. And three main strategies they say. One is linear upper bound strategy. So if we see the graph, it basically says how it assigns weight. In case of linear upper bound, it gives more weight to the high loss samples and it down samples the low loss values. In case of quadratic, it gives more weight to the medium loss samples. In case of extreme, it gives weights to the low loss as well as high loss samples. And after calculating this SI, we have to use softmax to normalize it. So that delta t. So if we see the delta t, that is nothing but a 1 by m minus weight we give to each and every sample based upon the theta t multiplied between the gap. The click here. So that basically have the weight term we give to each and every sample, and the second term is nothing but a gap between the optimal theta star and the one at time step t. So here, if we see if the gap is high, sorry, if a gap is low, which means the model, the sample is easy sample. So we need to give lower weight to it. That will reduce the bound. So that's the main relation over here, and they come up with this. So they're assuming it holds, and they are with this. Just theoretically, they're assuming the theta star exists, and they're coming up with this thing. Like practically, we don't know, but theoretically, they're coming up with this.
All the time. You don't know.
No, sir. Theoretically, they saw this relation. So practically, they're coming up with these strategies to implement the weighing techniques.
Expression about all that.
Yeah.
Yes.
S we calculate first, and for a batch, and then we normalize it. Softmax is used.
Example, quite much.
No, sir. Here just
Here it's just batch set. There is no concept of microbatch here.
SI is for a single
Sample.
sample, so we calculate for a complete batch, and then we use softmax. No, sir.
W is softmax of SI.
To get the motivation, how the relation is, they took from the theorem and made up with the strategies to implement. And so this is how the thing is implemented. So as you're asking, like we should be using the reweighting after the model gets stabilized for some time. So here they basically does it. So if the R value is high, it is kind of goes to the uniform sampling. So initially in the training process, they do that. After a certain point, they go with the reweighting. They reduce the R value so that weights are being assigned. Like reweighting is done, and they do the pre-training process. Yeah. Also, this is fine grain. We can do it in along with the domain level. Like we give weights for domain also. We can do it domain level also. So that's what they've shown here. Yeah. So one major thing is smaller models. They have seen some less improvement compared to the larger model. And again, they're not actually dealing with a noisy sample. They said implicitly it just being addressed. That's it. So the conclusion is giving weights to based upon the loss value indeed helping the LLM pre-training, and we can go with fine grain plus coarse domain level adjustment. But all of this method were lacking principal way of going with handling the noisy sample and the hard sample. So in the project we are based. Yeah. Step 5. Uh-huh. So that is within a batch. So minimum loss value and the max and they're just normalizing. um, that particular theorem, they like they're like theoretically they're seeing how the weights and the loss is dependent, like how they are being relation. So they're saying if the loss gap is less, which means the sample is being learned well. So we need to give lesser weight to that. Uh, um, So what I understood is when we see this delta t, so if the um, gap is small, like if you're going with a uniform sampling, there is no weight over there, then it will be just 1 by m multiplied by the gap. So since the weight is being added, the strategies, I think they never mentioned any relation with how they come up with, they just devised it by giving sometime importance to the moderate loss, sometime importance to the low loss, like that. But HI is a normalized loss. So coming to the project, we are basically dealing with this only using model uncertainty methods. We are principally handling the noise difficult and easy sample here. Initial run has been done, but it's not of as expected result, so we're improving upon it. So we have used GPT 270.
Yes.
Yeah.
Yes.